Welcome, engineers, to a deep dive into an often overlooked yet critical aspect of modern software development, container image optimization for production Kubernetes. Today, we're not just talking theory, we're uncovering practical strategies that define success in enterprise-level deployments. By the end of this lesson, you won't just know what image optimization is, but why it's indispensable for your production systems. You'll gain a solid understanding of how optimized images lead to substantial cost savings and performance gains, a concept often underestimated. We'll then break down the mechanics of Docker layer caching, equipping you with the knowledge to drastically accelerate your CI/CD pipelines. You'll learn the enterprise standard, implementing multi-stage builds and making informed decisions about base image selection, balancing security with efficiency. Finally, we'll connect these technical details to their real-world impact, showing how optimized images improve deployment velocity, reduce cluster costs, and enhance overall security. Let's get started. You might think a few extra megabytes in an image are negligible, but at scale, these hidden costs become enormous. Imagine a 500 megabyte image deployed across 10,000 pods in a large social network. That's 5 terabytes of unnecessary network transfer every single deployment. Companies like Spotify have seen their deployment times slashed by over 70% and saved hundreds of thousands annually simply by optimizing average image sizes. The real impact isn't just storage, it's velocity. Every additional 100 megabytes can add 12 to 15 seconds to pod startup time in Kubernetes. During a traffic spike, those seconds directly translate to dropped requests and potential revenue loss. A major travel platform found that by optimizing their Python service images from over a gigabyte down to 180 megabytes, they improved their scale-out time from 47 seconds to just 8 seconds, directly improving their service level agreement compliance. And for your CI/CD pipelines, understanding Docker's layer invalidation mechanics can transform build times from 20 minutes down to 2. This is where layer caching becomes your secret weapon. At the heart of efficient container builds is Docker's layer architecture. Think of a Docker image as a stack of immutable cached layers, much like a file system. Every instruction in your Docker file, whether it's a run command or a copy instruction, creates a new layer. The magic happens with Docker's build cache. If a layer and its parent haven't changed, Docker reuses the cached version instead of rebuilding it. The critical insight here is that layer order directly determines how efficiently this cache is utilized. Consider the anti-pattern, copying all your application code before installing dependencies. If you change even a single line of code, the copy./app instruction invalidates the cache for all subsequent layers, including your pip install or npm install command. This forces a full dependency reinstallation on every single code change, turning an 8-second build into a 3-minute wait. The production pattern flips this. Install your stable dependencies first, then copy your application code. Now, dependency installation only runs when your requirements.txt or package.json actually changes. This simple reordering means your typical code change builds in mere seconds, not minutes, dramatically improving developer iteration speed. Moving beyond layer ordering, multi-stage builds are the enterprise standard for production-grade images. The problem with single-stage builds is they often include heavy build tools like compilers, development headers, and testing frameworks that are essential during compilation, but completely unnecessary at runtime. This can balloon a Python image from 180 megabytes to over a gigabyte. Multi-stage builds solve this by defining separate builder and runtime stages. The builder stage compiles your application, installs dependencies, and generates artifacts. The runtime stage then only copies the necessary artifacts from the builder, discarding all the heavy build tools. This drastically reduces your final image size, improving cluster bin packing efficiency, as seen at companies like Google. Next, your base image selection is a critical trade-off between security and size. While Alpine offers maximum compatibility, it comes with a larger attack surface and hundreds of potential CVEs. Ubuntu provides maximum compatibility but comes with a larger attack surface. For ultimate security, distroless images remove the shell and package manager entirely, making them incredibly secure but harder to debug. And for static binaries like Go or Rust, Scratch offers zero overhead. Finally, to supercharge your CI/CD, leverage BuildKit's cache mounts. This feature allows you to persist package manager caches like pip or npm across builds, reducing dependency resolution times from minutes to mere seconds, even if your requirements change. Now, let's bring it all together and look at the real-world impact of these optimizations. At scale, image pull time is a critical component of pod startup. Imagine scaling out from 50 to 500 pods. A 1 GB image could mean thousands of seconds of cumulative pull time. Optimized, smaller images drastically reduce this, leading to 700% improvements in scale-out responsiveness and faster recovery during failures. Beyond performance, there are tangible cost savings. Registry storage isn't free. An organization with hundreds of microservices can spend thousands annually on bloated image storage. Optimizing images can cut these costs by 80% or more. Security is another massive win. Vulnerability scanners spend less time on fewer layers, and minimal base images like distroless eliminate 95% of common CVEs, streamlining your compliance and security reviews. Leading companies like Netflix and Stripe treat image optimization as a continuous process, not a one-time task. They enforce multi-stage builds via policy as code, standardize base images, and use automated layer analysis. This isn't just about building better containers, it's about building better systems that are faster, more secure, and more cost-effective. As a final thought, consider this. How does understanding Docker's layer invalidation and proper layer ordering directly impact your CI/CD velocity? Reflect on that, and you'll grasp the core insight of today's lesson. Tomorrow, we'll build on this foundation by diving into container networking, exploring how these optimized images communicate across your service mesh.